In this section, we cover an idea that's probably already understood by you intuitionally, and that's the idea of continuity. However, it is fundamental to calculus and mathematics in general, this idea of continuity. And so it's important that we understand the, how should I say, the definition of continuity so that we can work with it and make sure that we understand exactly what we're talking about when someone says the word, this function is continuous or something like that. So first off, let's kind of draw a graph of a function that I would say is continuous. And so a function is, say, continuous. The layman's idea of it would be that I could draw it without ever lifting my pen. So this graph, this function, I would say, is continuous. There's no jumps in it, there's no asymptotes, there's no holes. So if that's a continuous function, that's probably what, when you picture the graph of a function, this is probably what you envision. So what can go wrong? So one thing that could happen, I could have what we call a jump discontinuity. Say my function is defined here, but maybe at this point there's a jump. Maybe right here it jumps and then goes like this. So to the left of this spot, it's continuous, nice and smooth. To the right of it, it's continuous, but we have a jump here. And if I were to, well, first let me tell you what we would call this a jump discontinuity. And if I were to bring out my infinitesimal magnifying glass, I could zoom in here, and I could zoom in at this point, and then finally I could zoom in at, say, this point, and we could see how the graph would look. Up here at the first one, right, we'd have our function, it comes along and then kind of stops. Over here, when we zoom into a point, we just see that single point, and then over here, if we zoomed in, right, the graph would come along and it stops. So we can see it at the infinitesimal level, we can see it in the macro level, that if I were to draw this graph, I would stop here, have to lift my pen, put a dot there, lift my pen, and then draw it on. So that is what we would call a jump discontinuity. Another kind of discontinuity would be a point discontinuity. So here, come along, and maybe there's a hole in my graph, somewhere where it's undefined. And it could even be, actually it could be defined. We could have a value there. Again, if I zoom in at this point, so if I zoom in here, looking at the infinitesimal level, or I zoom in here, looking at the infinitesimal level, we've got two different kind of behaviors at this point of discontinuity. So here, the graph comes along, and then there's a hole, and then continues on its merry way. Whereas up here, we would just see a point floating by itself in space. So up here, we've got a point, down here, we've got a hole, and this is what we would call a point discontinuity. And the third final type of discontinuity is an asymptotic discontinuity. So maybe I've got an asymptote, let's say right here, I've got some kind of asymptote, and the graph, if I look at it from the left, maybe comes along and approaches this asymptote but never touches it, and coming from the other direction, maybe it comes like this. And so at this point, C, I can still zoom in, and so if I zoom in here, I zoom in here, I would get, well, I'd still see my asymptote. So I'd still have my asymptote, and my function, or the graph, would just be getting real close to it, but never actually touching it. And similar on the other side, I can zoom in here, and we would see the same behavior. Right? But instead of it being on the right-hand side, in this case, my graph would be approaching it from the left. So it would be very close to it, but not equal to it. And so my graph would look something like that if I zoomed in. And so this is what we would call an asymptotic discontinuity. Let me kind of get that so we can read it. An asymptotic discontinuity. So these are, as I said, continuous functions. Again, your intuition is that it's nice and smooth, there's no jumps, no points of holes, no asymptotic behavior. So well-behaved function. The majority of the functions you've worked with in your mathematical career have been nice continuous functions. Every once in a while, maybe you run into a piecewise function in which we've got jumps or holes. Rational functions will have holes oftentimes, or 1 over x has a nice discontinuity. So that's our intuition. The intuition you should have for a continuous function. So let's get on the screen exactly what we mean by a continuous function formally. So a function is continuous at a point c if f is defined at c, and if whenever x is infinitely close to c, then we have that f is infinitesimally close to c. Now, other ways of describing this would be that if the, say, the standard part of x is c, then the standard part of f of x is f of c. Or, using our limit definitions from the previous section, we could say that the limit as x approaches c of f of x is equal to f of c. And in fact, this is the standard definition you would see in most textbooks. Right here is the standard definition of continuity. It's all about limits. And again, because in a typical calculus class, everything's described in limits. Here we've got ideas of standard part. As we talked about in the last video, standard parts and limits go hand in hand. They're one and the same. They're just different ways of seeing the same ideas. So another way, so we could think about standard parts, we could think about it as limits. This business here about standard parts, so again, these are all equivalent ways of talking about continuous. We could say, well, if another way to characterize continuity is if delta x is an infinitesimal, so it's some infinitesimal number, then delta y, remember, which is f of c plus delta x minus f of c, is also infinitesimal. And why should that be the case? Well, let's say that delta x is an infinitesimal, then c plus delta x is an infinitesimal. Right? So if delta x is an infinitesimal, then c plus delta x is infinitesimally close to c, and if delta y is an infinitesimal, then, well, delta y, so f c plus delta x minus f of x is an infinitesimal, so we have that f of c plus delta x would be infinitely close to f of c, which is exactly what we have here. So these are all kind of equivalents, and in fact there's 6 equivalent statements. Let me post them up here so we know exactly when we have or different ways of checking to see if a function or relationship is continuous. So we call it a theorem, but what we're just saying is that if y equals f of x and f of x is defined at c, so that's one of the key components of being continuous. It's got to be defined. In fact, let's stress that. F is continuous at a point c if it's defined there. So it's got to be, first off, it's got to be defined. So our theorem states, okay, well, if we've got a function that's defined at c, then the following statements are equivalent. That is, if any one of the statements is true, all of the other are true as well. So f being continuous c, if x is infinitely close to c, f of x is infinitely close to f of c. The standard part of x is c, then the standard part of f of x is f of c. The limit as x approaches c of f of x is f of c. Y is continuous c, that's kind of repeating this. And if delta x is infinitesimal, then delta y is infinitesimal. So these are all equivalent. So if I say continuous, if f is continuous, you can say, okay, I know every single one of these statements are true. In the examples that follow, we'll see that we'll use these ideas. Now, something that may not seem obvious right off the bat would be the connection between a function being continuous and the differentiability of a function. But remember that if, say, f prime of c exists, so it's differentiable at this point, then we know that delta y can be written as f prime of c times delta x plus epsilon times delta x, where delta x is an infinitesimal and epsilon is an infinitesimal. This is the increment theorem. So notice what we have. So then if delta x is an infinitesimal, delta y is an infinitesimal, and from theorem 1 we have that, well, if delta x is an infinitesimal, then delta y is an infinitesimal, and if we have that being true, then this right off the bat tells us then that f is continuous at c, which gives us a second theorem. But this theorem is only goes one direction. It only just says if f is differentiable, that is, if f prime exists, then f is continuous. F being continuous doesn't mean that the derivative exists. And a prime example would be the square root function. So if I look at its graph, which looks like something like this, right? This is the graph of y equals the square root of x. We could formally see it's continuous, but let's just take it on faith, right? This is what the graph looks like, so there's no holes, there's no jumps, there's no asymptotes. So this is a continuous function everywhere. In particular, it's continuous at 0. In fact, we know that if, say, h is infinitely close to 0, then the standard part of the square root function is equal to the square root of the standard part of x, which is the standard part of 0, which is 0. So the standard part is equal to, right, this is the square root, I'll just rewrite it, square root of 0. So it, by the basic definition, it is continuous at 0. However, we take its derivative, dy dx is equal to 1 over 2 square root of x. And that means that dy dx of 0 does not exist, right? Because we would be dividing by 0. So we've got a continuous function at 0, but it's not differentiable at 0. So keep that in your head, that this theorem only goes one way. That if it's differentiable, then it must be continuous. But if it's continuous, it might not be differentiable. In fact, let me make a little box here of how this breaks down. So I can have, maybe this would be the set of all real functions. So this would be my space. This would be all real functions. Then inside of this would be the set of all continuous functions. So not all real functions are continuous. So we have a smaller group of all continuous functions. And then inside of that we have a smaller group of all differentiable functions. Right? So this is kind of a nesting of the function space. We can have all real functions, so this box is representing all real functions in all the universe. Inside of that is a smaller subset of all continuous functions, and inside of that is a smaller subset, all differentiable functions. So this kind of gives you a sense of how the universe of functions breaks down. It's grouped into these things. What else is preserved by continuity, right? If I have two continuous functions, what else do I know? Well, theorem 3 states that if I've got two continuous functions, if I know somehow that they're continuous, then I can take a product with a constant, it's still continuous. I can add or subtract two continuous functions, still continuous. If I multiply two continuous functions, it's continuous. If the denominator is not 0, then the ratio is continuous. If this is in the domain of the root function, then the root function is continuous. All these, I'm not going to prove these, but all of them fall quite naturally from the fact that the standard part distributes across addition, across multiplication, across ratios, across roots. Similarly, as we saw last section, limits distribute across all these. So since continuity is related to the standard part or related to the limits, it should be somewhat clear that this theorem is true. So students, always the very next question in this kind of list of things is what functions do I know right off the bat? Do I just can take for granted are continuous? And so let me here post the list. So when it comes to continuous functions, what functions are continuous? Well, polynomials. Every polynomial is continuous. All rational functions are continuous on their domain, which, what am I saying, means that I'm not dividing by 0, and the top's continuous. All exponential functions are continuous, which actually then by default gives us that their logarithms are continuous. All trigonometric functions are continuous again on their domain. So once you leave the domain, well, the function's not even defined, and so if the function's not defined, then it can't be continuous. So in the next video, this video we were just kind of looking at all the theoretical ideas of continuity. What does it mean to be continuous? What functions are continuous? There's a lot of stuff running at you. In the next videos, we'll look at some examples of defining the set of points in which a function might be continuous.